Alright, thanks for watching and welcome to another exciting Fibonacci episode, or shall I say, Fibonacci-sode. Aha! So previously in Payam Battlestar Galactica, we solved for the Fibonacci sequence using linear algebra, but today we will do this using pure calculus. In particular, we will use power series. And you'll see it's elementary, but definitely not easy. Okay, so let me just remind you of the Fibonacci sequence. It's given by un equals to un plus minus 1 plus un minus 2. In other words, the present is given by the sum of the two pasts, or another way of seeing this is the future in two steps is the present term plus the next term. And we're also given initial conditions. And in this case, let's take the conditions u0 equals to 0 and u1 equals to 1. And you might say, hey, it's not quite the same thing I wrote in the previous episode, but first of all, it makes the resulting formula easier. And also notice, if u0 is 0 and u1 is 1, then u2 will be 1. So eventually you do have this sequence 0, 1, 1, 2, 3, 5, 8, etc., etc. And as I said, this time we will use power series to solve it. So consider the following function, and don't ask me where I get this from. I asked the math smugglers and they gave me the secret ingredient. Let f of x be x over 1 minus x squared. But let me motivate this a little bit. The denominator will involve the golden ratio. So that's why we chose this polynomial. And also x makes a certain shift that makes this method work. Okay? So let f of x be this function, and suppose we can expand f as a power series. And in fact, we will do this later. Suppose you can write f in terms of the following: sum from 0 to infinity of un x to the n. For some un, United Nations, this is for you, okay? So suppose you can write f of x in terms of the power series. It turns out, and we will show this now, that the coefficients in fact satisfy the Fibonacci relation. Claim un satisfies un equals to un minus 1 plus un minus 2. So it's very interesting. In other words, if you expand f as a power series, it turns out this function is special enough that the coefficients satisfy the Fibonacci relation. So you can think of it as a Fibonacci function, if you like. And by the way, this can be cast in a more general process called the generating functions, but let's not go there. Let's keep it strictly calculusy, okay? All right, how do you do this? Well, let's start with this equation, right? X over 1 minus x squared. Suppose you can write this as a sum from 0 to infinity of un x to the n. And let's just cross multiply. So multiply this chunk and this chunk together, and x and 1 together, and let's see what we get. Then, indeed, we get that x equals to the sum from 0 to infinity of un x to the n times this polynomial, 1 minus x squared. Let's have another expansion party. This is the sum from 0 to infinity of un x to the n minus the sum from 0 to infinity of un x to the n plus 1. So x to the n times x is x to the n plus 1. So minus sum from 0 to infinity un x to the n plus 2. And well, notice we have x to the n plus 1, x to the n plus 2. Those things cannot really agree, but let's write those sums such that we have x to the n on each side. Because then we can factor stuff out. But notice, if you write this sum out, it's minus u0 x to the 1 minus u1 x squared minus blah blah blah. So this middle sum, you can write this in the following form. Sum from n equals to 1 to infinity of x to the n. And notice this index here is always 1 less than the power of x. So we get u to the n minus 1, x to the n. And what about here? We get minus u0 x squared minus u1 x cubed, etc., etc. So here, the index is 2 less than the power of x. So sum from n equals to 2 to infinity of un minus 2 x to the n. And lastly, this thing is still the same. Sum from 0 to infinity of un x to the n. And now, we can almost factor stuff this x to the n out, except we have another problem. So we created a problem by solving one. The problem is, all those things, those sums, they start at different numbers. So let's just make them start at the correct number, namely 2. So let's discard all the terms until we get the term 2. So the n equal to 0 term becomes u0 x to the 0, so which is 1. The next term is u1 x, and then in fact the sum starts at 2. Sum from 2 to infinity un x to the n. And let's do the same spiel here. Okay, so minus u0 x minus sum from n equals to 2 to infinity un minus 1 x to the n. And finally the sum that we like here, sum from 2 to infinity un minus 2 x to the n. And this is very good because other than this junk here, we have the sums that start at the same number, 2, and we have x to the n, which tells us we can factor this sum out. So let's write this a little bit. So it's u0 plus, why not, let's factor x out, u1 minus u0x, and then plus, put everything inside of the sum, we get un minus un minus 1 minus un minus 2 x to the n. And now let's look at the inequality. We have junk, explosion, blah blah, expansion, woo, yay, 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 pi m, okay, equals to this. But what's that equal to? It equals to x. So let me write this x in a more suggestive way. That's 0 plus 1x plus just sums of zeros. 0x to the n. In particular, if you compare those coefficients, we get that u0 is 0. u1 is u0 plus 1, which is 1. And more interestingly, we get this term is also 0, which will ultimately give us our desired equation. So we get u0 equals to 0, u1 minus u0 equals to 1, which tells you that u1 is u0 plus 1, which is 1. And lastly, we have un minus un minus 1 minus un minus 2 equals to 0, which in fact gives us the Fibonacci shift, the Fibonacci relationship. Okay, really cool. What have we shown? We've shown that in fact, maybe the next step, if you can write x over 1 minus x squared as a power series, so sum from 0 to infinity of u and x to the n, then in fact the coefficients satisfy the Fibonacci relationship. So all you have to do is indeed write this as a power series, because by the previous step it tells us that the coefficients are the key to solving our problem. So let's find this. WTF, want to find. Okay. And how do we do this? Well, this is a rational function, and usually it's a good idea to partially fractate things. And for this, notice the following. Okay. This denominator, you can factor it out in the following way. 1 minus x squared, it's minus x squared plus x minus 1. And the cool thing is, let's erase that, that you can actually factor it out in terms of almost the golden ratio, so not quite. If we use the quadratic formula, we get in fact that, you can factor this out in terms of the following, where a is minus 1 minus square root of 5 over 2, and b is minus 1 plus square root of 5 over 2. So remember this, we will use those definitions at the end, but the point is you can factor it out in this way, and careful, this is not quite the golden ratio. So it actually took me an hour to figure out that it's not quite the same. But this is behind the scenes if you want. And just a little thing, you can actually flip this. X minus a becomes a minus x, and x minus b is b minus x. And in fact, it's not a problem because you're doing this twice. So the point is, you can write 1 minus x squared in this way, and I'll explain in a second why this is useful to write it in this way. Okay, so the next step is to partially fractate this, because again we have a rational function. What does partial fraction say? We want to find a and b such that the following is true. So our function x over 1 minus x squared, which you can write this in the following form by our factorization, a minus x times b minus x, and you have this x, except we also have the minus sign, which you can put on top. And ideally, this rational function, we want to write this in terms of capital A over a minus x plus capital B over b minus x. And the reason is, once we do that, those look like geometric series, so we can just easily find the geometric series. And that's why I also put it as a minus x and not x minus a, just to make our lives easier. And in order to do that, let's put this on a common denominator. So you have a times b minus x plus b times a minus x over a minus x times b minus x, another expansion party, so ab minus ax plus ba minus bx over a minus x times b minus x. By the way, British Airways, if you're watching, this is for you. So BA. And And then let's group everything in terms of the powers. So here we have a power of x, or if you want just a constant power first. So AB plus BA, okay, plus minus A minus BX over A minus X times B minus X. And you want this to be equal to minus X. So if you want 0 minus X divided by this chunk. So, in particular, comparing, first of all, the coefficients of X, we get minus A minus B equals to minus 1. And comparing the constant coefficients, this thing, okay, we get AB plus BA equals to 0. And so let's solve this a little bit. So if you want, we get, A plus B equals to minus 1. So B is minus 1 minus A. Okay, sorry, A plus B equals to 1, my bad. So B is 1 minus A, which makes stuff easier in the end. And then, from this and the fact that B equals to 1 minus A, we get AB plus 1 minus AA equals to 0. And from this we can solve for capital A. So AB plus little a minus AA equals to 0. So A times B minus A equals to minus A. So capital A is minus A over B minus A. And remember, small a and small b, they're given in terms of the golden ratio. And it turns out, if you calculate 1 minus A, you get simply B over B minus A. So the point is, capital A and capital B are now found in terms of constants that we know. And once we have that, let's solve our power series problem. Okay, so now we have x over 1 minus x squared is capital A over A minus x plus capital B over B minus x. And remember, those are now constants that are known. We know capital A, we know capital B, we know little a and little b. And let's just write those things as a power series, because if you think about it, you may recognize this as geometric series, because if you factor out little a, you get a times 1 minus x over little a plus b times little b of 1 minus x over little b. I don't know, isn't there a rapper called Little B or something? Well, this is for you, Little B. Okay, and now, remember, the nice thing is that 1 over 1 minus r is just the sum of rn's from 0 to infinity. This is the geometric series. So in particular, this becomes a over little a of sum from 0 to infinity. Here r is x over a, so x over a to the nth power, plus b over little b times sum from 0 to infinity of x over b to the n. Well, it's kind of pretty how, those ratios are sort of appearing, but let's make it even prettier by putting everything in terms of one sum. So that equals to the sum from 0 to infinity of a over little a. Okay. This becomes x to the n over a to the n. And let's pull out a little a over n here. And similarly with the other thing, b over b times 1 over b to the n. And notice, both those things have a common factor of x to the n. So we have that. All right. And now we will unravel now our formulas. Remember, we can write capital A and capital B in terms of little a and little b. So we have the following sum from 0 to infinity of, remember, capital A is minus a over b minus a, and you're dividing this by a times a to the n. So you have this little cancellation plus b over b minus a over b to the n. It's like the B movie, but every time you say I write B, you get more confused. So the point is one of those B's cancel out, and in the end, you're left with the following. Turns out there's a nice simplification. First of all, there's a common factor of 1 over b minus a. Moreover, we have plus 1 over b to the n minus 1 over a to the n, which you can write it as follows. 1 over b to the n minus 1 over a to the n. And you still have the factor x to the n. Okay, this is all in good, but what have we done? Oh yeah, what have you done? We took the function x over 1 minus x squared, and lo and behold, we wrote this as a power series. So, in fact, the coefficients here are the coefficients of the power series, and that's what we call un. So very excited un, okay? Not triple factorial. And so, all that's left to do is write this in terms of little a and little b, which are the constants that we know. So let's write this more explicitly, because it turns out there's a nice simplification. Okay, last step. So un, we know that it's 1 over b minus a, 1 over b to the n, minus 1 over a to the n. Okay, let's calculate this. 1 over b minus a, that's 1 over minus 1 plus square root of 5 over 2 minus, so in other words, yeah, minus 1 minus square root of 5 over 2. And the nice thing is, you have a minus 1/2, which cancels out with this minus 1/2, and you get 1 over square root of 5 over 2 plus square root of 5 over 2, which is 1 over square root of 5. Turns out it's a nice simplification. And similar for b, 1 over b, this just becomes, so 1 over b, b is 1 over minus 1 plus square root of 5 over 2, 1 over minus 1 plus square root of 5 over 2, and it's 2 over minus 1 plus square root of 5. And you know, whenever in school they tell you it's bad to have a square root on the denominator, it's precisely because if you actually rationalize the denominator, you get a nice simplification. So let's just multiply this by the conjugate form. So 1 minus 1 minus square root of 5. And you're left with, so if you want, minus 2, 2 times minus 1 minus square root of 5. And this becomes minus 1 squared minus square root of 5 squared. So minus 4, which tells us that, first of all, this 4 becomes 2. Aha, 42. And those minuses become pluses. So we get 1 plus square root of 5 over 2. So after this plastic surgery, we indeed get the golden ratio. It's like a facelift. And similarly for 1 over a, right, that It's 1 over minus 1 minus square root of 5 over 2. And that becomes minus 2 over 1 plus square root of 5 multiplied by the conjugate. And you're left with, again, minus 2 times 1 minus square root of 5. And here again you get a squared minus b squared. So you get minus 4. So the minus cancel out. 4 becomes 2. And you get 1 minus square root of 5 over 2. So after those simplifications, you indeed get that at the end, un equals to, going maybe here, 1 over b minus a. It's 1 over square root of 5. 1 over b to the n. It's the same as 1 over b to the n. 1 plus square root of 5 over 2 to the n. Minus 1 over a to the n, which is 1 minus square root of 5 over 2 to the n. And lo and behold, we get the formula for the Fibonacci sequence. Ta-da! And I didn't break my chalk, so good for me. And if you like that, and you want more Fibonacci extravaganzas, or if you like math in general, please make sure to subscribe to my channel. Thank you very much.